Welcome to the February Tech Forum. This is your opportunity, your monthly opportunity to kind of get together and learn about all things technical. This month we have a very special guest, Dr. Miguel Rodrigues, who's going to be talking about kind of the use of AI for artistic imagery. So, thank you. Take it away.
All right. Thank you so much, Tom. Thank you so much for the invitation to come and speak here. Right. So I'm not sure whether you have come across this painting before. This is a Vincent van Gogh painting, a patch of grass that was painted in Paris. Now, I mean, the question is, whether you have ever wondered what is beneath this particular painting. So what I'm going to talk about today is artificial intelligence for art investigation, in particular how techniques that underlie artificial intelligence that could range from machine learning to signal processing, image processing, information processing are supporting art historical investigation, conservation and preservation of artwork, which is a kind of topic which is perhaps orthogonal in some ways to what you do here, but you'll see that many of the techniques that we explore in various domains and we use in various domains to process data, they can also be used in this particular domain in here. Right, and well, the fact that paintings add various secrets that in a way they capture the public imagination and can attest to the creation history and the restoration history of a painting as often appeared in the news, as in the case, for example, of this 1589 portrait of Sir John Maitland, the Lord Chancellor of Scotland. So this has appeared a couple of months ago in BBC and various other media worldwide. And in particular, what upon X-ray examination of this painting, so this is the visual. Now, if you take an X-ray of this painting, what conservators and art historians have realized is that there is another painting underneath Maitland's painting, which relates to Mary, Queen of Scots. And this was an extremely exciting revelation because portraits of this queen are very rare. So essentially, within the field of art historical investigation, as well as conservation and preservation of art, what we are interested in, beyond, for example, trying to reveal concealed designs, is to carry out various other tasks that range, for example, the analysis of the style of artwork, authentication of artwork. This is something which is extremely important, for example, for auction houses, artwork provenance, attribution, and even dating. So that's another important aspect, as well as doing virtual restorations of artwork, so that can inform, for example, conservation and preservation treatments. And in addition to all that, so another important aspect is try to characterize the materials that are present in artwork, like the different pigments, the different binders that are used in artwork, because again, this can inform conservation and preservation treatments. In fact, many galleries worldwide, they've got specific departments that look at various of these particular problems. However, in order to be able to realize these particular tasks, it's also very important to understand what is the anatomy of a painting, and in particular, so in my case, I'm interested in old master paintings, so the anatomy of old master paintings. And these are extremely complex objects. For example, if you take a cross-section of a painting, what you will see is that this consists of various layers. So, for example, you've got first the support, such as the canvas, and on top of the canvas, painters, they often apply what we call a ground layer, which is necessary to support further paint passages. So you've got the ground layer. Following the ground layer, you have this preliminary sketches made by the artist, which kind of delineate what the artist is going to paint on top of the ground layer. And then you've got the different paint layers, right? These are just different layers of pigments and binders that the artist uses to produce the painting. And finally, at the very end, you apply, say, a varnish or glazes in order to preserve further the painting. Now, the ability to perform many of these art investigation tasks, as well as the ability to perform the ability to understand artwork also involves trying to understand some of these layers which are not directly visible to the naked eye. So in order to do that, people and people that study art, they have been developing a wide range of techniques. So one of them, for example, involves the invasive and destructive analysis of artwork. Now here, what people do is they take, say, very tiny samples of paintings, so often in areas that are already damaged, in order to try to understand, say, the stratigraphy or the different layers that are present in the painting, as well as the materials that are present in the painting. So this is a painting of Francisco de Goya, Dona Isabel de Portel, at the National Gallery. And here we've got a particular sample, a micro sample taken from this painting, from one of these red sleeves of this lady in the painting. And you can indeed see different layers. So you've got this red layer, which corresponds in fact to the red sleeve. But you also see other layers, such as a yellow layer below this red layer, as well as the orange ground type of layer. So that's a way of studying paintings, and people, they often resort to this way in order to understand paintings better. But another way that has been evolving for a number of years relates to the use of electromagnetic radiation. And here the idea is, by using electromagnetic radiation and different imaging devices, we'll be able to study artwork in a non-invasive and non-destructive type of way. So normally, to the naked eye, or the naked eye is sensitive to a certain range of frequencies within the electromagnetic spectrum that range from about 7 to 10 to the 14 Hertz to 4 to the 10 to the 14 Hertz. But above these frequencies and below these frequencies, there's many other that can illuminate or provide us a different view of artwork. So, for example, we've got gamma rays, X-rays, and ultraviolet radiation with frequencies higher than those corresponding to visible light. But we also have infrared microwaves and radio waves whose frequencies are well below the frequency of visible light. So the idea is, due to the fact that some of these, such as, for example, X-rays, this is high energy radiation with the ability to penetrate through, say, different layers. So due to this ability, the rationale is, by using this type of radiations, we should be able to understand better the anatomy of an old master painting. Right, with this in mind, so over the years, a number of imaging and analytical techniques have been proposed to study artwork, as well as many other phenomena. And this kind of started in 1895 with the discovery of X-rays by Röntgen. And in fact, one of the very first shadowgraphs that he has produced was of a painted surface. Now, in the 30s, people started using X-rays or X-radiography in museums. This was followed by the use of ultraviolet-induced visible fluorescence, followed by infrared reflectography in around the 60s. And since then, a number of more sophisticated imaging techniques have been introduced to study artwork. So, for example, around the 90s through 2000 and more recently, people start using multispectral and hyperspectral instruments. In fact, part of the motivation is many of these instruments are in fact used in Earth observations. So many satellites, for example, they've got this type of cameras in order to understand, for example, the materials in the Earth. And in the same way, so people thought that this type of instruments, they could also be used to understand and study artwork. So, for example, many of these instruments now are used in a routine type of way in galleries worldwide. For example, the National Gallery of Washington has developed a few years back an hyperspectral instrument to analyze their paintings, and they have produced a range of beautiful papers that show how hyperspectral imaging can in fact inform the technical study of art as well as conservation and preservation of art. And the National Gallery here in London is now developing one of these instruments as well to study their artwork. Now, in addition to that, we also have X-ray fluorescence. So this is another emerging technique that can be used to study artwork and try to understand the materials and features within artwork. And there's a range of many other techniques that are being used nowadays or are being developed as we speak in order to be applied to this particular domain. I mean, this can be applied, say, to paintings, but also is applied to many other cultural heritage objects. So, X-ray and infrared imaging. So again here, so we've got this color photograph of Donna Isabel de Portel, a painting in the National Gallery. And here we've got the X-ray corresponding to this painting and the infrared image corresponding to this painting. And what you can see is, due to the high penetration of X-rays, so X-rays can really probe within the surface. And in this particular case, you can see that below the surface, you have another painting which corresponds to a male figure, which we do not quite understand who he is. So, I mean, there's some interesting art historical problems here. And in infrared, also, infrared reflectography also kind of unveils the presence of this subsurface feature. And in particular, art historians and art conservators, they are also very interested in infrared reflectography because one of the ability of this imaging modality is to reveal preparatory sketches within the painting. So these are often, these often reflect infrared light, and therefore this can be used to understand this. Now, more recently, so as I mentioned, there's two other particular imaging devices that are used in galleries or are beginning to be used in some of the leading galleries worldwide. One of them is X-ray fluorescence. So in X-ray fluorescence, what happens is the following. So you've got the scanner that is kind of probing the different pixels within a painting, and it bombards each of these pixels using X-rays. Now, the end result is the following. So there's materials within the painting or, in the different pixels of the painting. And when this is hit by an X-ray, so you will cause, electrons in the different atoms to go from a low level to a high energy level. Now, eventually, these electrons are going to come back to the low energy level, and that process will entail generation of a photon, right? Now, depending on the materials present in the painting and the different elements present within the painting, what you are going to observe for each particular pixel of the painting is going to be some kind of signature. And this signature is going to kind of indicate the different elements that are present in that pixel, and thereby you will be able to infer, say, the different pigments that are present also in the painting. So in fact, what this type of devices produce is a kind of data cube, an XRF data cube, where you've got an image, but there's also depth, and this depth relates to the signatures at the different energy or the different energy levels associated with this particular spectral signature per pixel. Now, this is revolutionizing the study of art and the conservation of art. One of the drawbacks of this particular technique is that it doesn't is unable to capture or organic compounds. So it doesn't see, for example, the element carbon. Hyperspectral imaging, on the other hand, can reveal those particular elements. And here, whereas, for example, Xray techniques, they kind of understand the elements that are present within the different pixels of a painting. So here we can understand the actual materials. So hyperspectral imaging uses, say, infrared and below infrared light to try to understand the painting. And it interacts with materials in diverse ways, in particular with its atomic structure, with the way that the different molecules vibrate. And the reflection that you're going to get back will depend on the molecular structure of the different materials. So again, this is going to produce spectra, right? And depending on the spectra that you are going to observe, you should, in principle, be able to understand what are the different materials that are present in the different pixels of the painting. So again, this is going to produce a data cube. And in this data cube, so on the vertical horizontal axis, you've got different images of the painting associated with different wavelengths of, say, this particular imaging modality. Right. Now, the availability, or the key issue here is the following. This is extremely useful to try to understand paintings and to support art conservation and preservation, but also in the process you are going to produce digital images of paintings. And by producing all this digital data, that also offers a unique opportunity for you to use digital technology to try to support art historical investigation and art investigation. So, for example, many of the fields that now are trying to get into this area include, for example, applied mathematics, statistics, time frequency analysis. There's computer science, machine learning, and there's also, for example, engineering, signal and image processing. And in fact, one of the very early initiatives that has recognized the potential of having this digital data of paintings was the Gogh Project. And within this project, a couple of colleagues, so what they have secured was near unprecedented access to high-resolution scans of more than 100 paintings of the Dutch painter. And the idea was to try to use this digital data and these scans to try to understand the artist's technique, as well as his brushwork, composition, and the way that the artist was choosing colors. But all these enabled through image processing technology, signal processing technology, and machine learning as well. In fact, one of the leading societies, Artie Police, I'm not sure whether you're familiar, but this is a leading society in electronic and electrical engineering. They have also recognized this opportunity. And in 2008, the ITV Signal Processing magazine, so what they have done is they have produced a series of articles, or they have invited a number of people to produce a series of articles reporting on recent advances on signal and image processing for art investigation. So here there were a number of articles covering topics such as new image acquisition equipment, in particular multispectral image acquisition equipment, as well as image manipulation technology to try to understand, for example, how to derive knowledge from the digital data that they were able to acquire from a painting. So here there were articles on artwork analysis, including the identification of artists, as well as the analysis of the brushwork, in particular brushwork of Van Gogh. More recently, and here I'm talking about 2 years back, 2015, there was another issue dedicated to signal processing for art investigation, where, again, so a number of articles were being invited to report advances in this field. And here we had like a number of papers covering, for example, topics such as canvas with analysis, so the analysis of the canvas. And this is extremely important for a number of reasons, for attribution analysis, for authentication of paintings, for example. There were articles as well on producing virtual restorations of paintings. or, for example, the style analysis of artists and paintings. Right. Now, what we are observing nowadays is that with the advent of many of these image acquisition technology, and in particular, hyperspectral imaging and X-ray fluorescence, is that we have access to huge amounts of data. So, for example, a hyperspectral data cube contains approximately 600 gigabytes per meter square, of painting area, whereas an XRF data cube contains about 20 gigabytes or so per meter square. And what this means is that there is a unique opportunity to explore this wealth of data to try to make sense of artwork. However, this also comes with many challenges, and one of them is how do we actually make sense of this wealth of data in order to solve important problems in art investigation. And this is exactly where artificial intelligence starts, in the sense that what many of the emerging artificial intelligence type of tools, powered, for example, by emerging machine learning methods such as deep learning, is that they provide you with the ability to find very complex relationships within data sets. This is certainly the case of deep learning, which is now being used for a very wide range of problems, from self-driving cars to image recognition to speech recognition. So very much the state of the art in, say, computer vision, image processing, signal processing, and beyond is powered by deep learning architectures. And again, so here the rationale is in the same way that these techniques can produce state-of-the-art results in other domains, so maybe we can also exploit these techniques to produce the cutting edge in art investigation, because we have the ingredients. So we've got massive data sets to produce insights, but also there's massive computational power, which is needed to power many of these algorithms. So what I'll be showing next is a series of problems that we have been working on, and some of my collaborators have been working on too, on how to use advances in artificial intelligence, from deep learning to many others, to try to address emerging problems in art investigation. Now, the first one I would like to show relates to AI supporting the technical study of art. And in particular, this is something that I've been recently involved in, and it relates to the well-known Ghent altarpiece, which is a very large and complex 15th century Flemish altarpiece produced by the Van Eyck brothers, Hubert and Jan van Eyck. And it's considered to be an extremely important painting for various reasons. Anyway, so this painting has been undergoing a massive restoration campaign recently. And the way that this altarpiece works is the following. So, I mean, there's this closed view where you kind of close the different panels. So in non-festive days, so this lies in a church in Belgium, in Ghent in particular. And on non-festive days, so the panels used to be closed. So you have this particular configuration, the closed view. But on festive days, so when there was some kind of important event, they would open the altarpiece, and you've got this particular configuration. Now, the problem that has been presented to us was the following. So in order to support the restoration campaign of this particular altarpiece, lots of data was being captured about this altarpiece. For example, so here you have the two views, and on this particular panel, so I mean that's this depicts Eve. You've got the figure of Eve, but because some of these panels are painted on both sides, on the other side you've got the angel. So corresponding to this particular area of the face of Eve, you have, say, the vest of an angel on the other side. Now, the problem that this is going to create is the following. If you take an X-ray, due to the high penetration of X-rays, so what you get is you are going to get a superposition of, say, the X-rays associated with the front and the back panel. And of course, this is not good enough for art restaurators because they would like to be able to unmix these particular X-rays. So what we have done is we have developed a set of techniques that are able to ingest lots of data, and then they attempt to unmix the X-rays. So these are some representative results. So these are the visuals. So this corresponds to it. This corresponds to the vest of the angel on the other side of the panel. And this is the mixed X-ray per se. And we are producing two sets of results. And on top here, we've got a state-of-the-art technique that does not quite mix the X-rays. So you can see that the eye corresponding to Eve appears on both of the, the X-rays that we're trying to separate. Whereas our technique produces far much better results. And again, so this is powered by many of these emerging methods that ingest a lot of data, and then based on this data, they try to find complex relationships among the data sets in order to produce the desired result. So this is a particular problem that has been studied. Another one relates to AI supporting the conservation of art, and this has been done by a collaborator of mine. And so the idea here was the following. So they want to restore certain panels which have degraded and aged over time. And in the process, again, so they take all this data from X-rays to infrared in order to support conservation purposes. Now, the problem that they were faced with here was try to identify areas of degradation or areas that have degraded or lost paint over time. So here we've got the visual of Prophet Zechariah, and what we've got here is particular algorithms that try to detect loss in paint. But this in a completely automated manner, and also using deep learning type of approaches to do this. This is something that is extremely useful, for example, for some of these art conservators. And the final problem that I would like to show is AI supporting new public experiences in art galleries. And this relates to the Gizzi altarpiece. Now, this has an extremely interesting story in the sense that altarpieces at some point in time, so this corresponds to, there's a series of panels here, and at some point in time, these altarpieces were being sewn, and then the different pieces were, being sold all over to people that were interested in buying, typically wealthy people. Now, this particular one, different pieces, they have been sold in various places, and at some point, the North Carolina Museum of Art was very interested in running an exhibition that brings together all these panels in order to show how this altarpiece looked originally. The challenge that they were faced with was that all panels were present except panel 9. So panel 9 has been lost. So no one knows where panel 9 is. So what they have done is they have invited these artists to come, and based on knowledge of the materials that were being used at this particular point in time when this particular altarpiece was being done, as well as based on historical knowledge, this artist, she has painted a particular form of this panel, which may not be completely accurate, but it's something that would be reasonably accurate using the same materials that were being used at the time. And they have produced the following. So here we've got two versions, or virtual versions, of this altarpiece. So there's the top one. So in the top one, we've got, so I'm not sure where So in the top one, we've got a virtual montage. But this virtual montage is one where we have the old versions of the panel, so the original versions of the panel. So you can see that if you compare one to the other, so the panels here look much darker than here. So what they have done was the following. They have learned the relationship. Of course, the new painting that has been produced was very shiny because it did not undergo degradation over time, whereas the original ones, they have undergone degradation over time and they have aged over time. So they have learned the relationship between, say, old panels and new ones, and based on that, they were able to virtually age the panel that had been produced, the one at the very bottom there, but also they were able to virtually unage, let's put it that way, the old ones in order to produce a montage of what this particular altarpiece might have looked like in original times. So you could go to this museum and be confronted with these two particular versions of the altarpiece. So there was the original version with the different panels, the exact panels, but beside you had this montage which included, say, the aged version of the new panel, as well as another montage, virtual one, or a picture of this virtual montage that included the new versions of the unaged versions of this particular piece. Again, powered by emerging methods in, let's call it artificial intelligence. So this is reported in this particular booklet. Right, now, beyond that, so I think that artificial intelligence is producing amazing results in various fields, as well as, say, in art investigation. So here we've got a very interesting problem that is being enabled by the use of deep learning type of approaches and generative adversarial networks in particular. So consider, say, different photographs of London in this particular case, and take, for example, say, a composition of Kandinsky, and what we'd like to be able to do is, to transfer style from one to the other. So by using many of these emerging machine learning techniques, well, what we can nowadays produce, and these are highly non-trivial problems. People did not know how to do that exactly, even a few years back. So what we can produce now is versions of these photographs with a style that corresponds to this particular image here. I mean, some of you may have come across in deep art. So I mean, this is widely known. Not only in that, but in Rutgers University in the USA, so computers now, they can judge human creativity. So they have consumed lots of data, of paintings, relating to paintings. And what they have done is, they have produced a graph that, attempts to map the influence and the creativity of the artists associated with various paintings over time. So they can now produce this type of graph. Not only that, but in addition to this, again, powered by deep learning type of approaches, in fact, generative adversarial networks, which they called in this particular case, creative adversarial networks, computers now, they can generate artwork which, seems to be very close to human artwork. So this is, instances of artwork produced by this particular network, this creative adversarial network, right? So in fact, this is now raising all types of issues. So for example, something that people are discussing now, because it's not just in paintings. In Japan, for example, it appears that there was this machine, again, powered by deep learning type of approaches that has also produced poems, for example. So we are seeing instances of creativity all over. And DeepMind, for example, in the game of Go, now the machine was so successful that was able to come up with rules that people did not know. In fact, it appears that books are being rewritten with new rules that were kind of devised by AlphaGo as it was playing Go with the champion, Lee Sedol. But anyway, so this is now raising all types of issues, and one of them, for example, is copyright. So who should own the copyright? The machine or the creator of the machine, right? So it's all sorts of fascinating things, going on within this general field. Anyway, so this is very, very early stages. And some of the challenges that I'm mentioning here, they cut across various application areas. So one of them is we need multimodal learning algorithms. So these are algorithms that are able to ingest different data modalities, whatever they might be. So could be, for example, video, could be text, could be images, and produce understanding. So this is something that is still at the very early stages, and we do not yet quite know how to do it. In particular, deep learning algorithms with this particular capability. We also need, for example, transfer learning algorithms, so algorithms that kind of learn in one domain, but can transfer much of the knowledge that we have learned in one domain to another domain. So humans, apparently, they are very good at doing that. Machines are less good at doing that. And again, so the other aspect that needs to be developed, and we are starting to take some early steps in that direction, is unsupervised learning. So many of the successes of deep learning, these were done in a totally supervised way, in the sense that we give it huge data sets, but these huge data sets are also annotated. They are also labeled. So the computer knows what corresponds to what. Now, a more interesting problem, because it's not scalable to annotate data sets, is to develop unsupervised learning algorithms that can make sense of the data without annotation, without this human type of intervention. So again, so there's some very early steps around this area, very recent ones, about a few months back, on trying to develop techniques. So again, this is very coupled to multimodal deep learning, but techniques are being developed to address this type of problems. And I think that once we put all this together, so the availability of digital data, the availability of state-of-the-art algorithms, together with, say, augmented reality technology, can potentially give publics new experiences in art galleries, akin to the one that I've just shown, but probably more sophisticated ones as well. Now, coming back to the patch of grass that I've shown in the very early slide, well, so what people have done was the following. So they have used XRF, so X-ray fluorescence, in order to try to understand the different elements that are present in the painting. And what we've got here is maps associated with different elements. So we've got lead, we've got mercury, we've got antimonium, and so on. So based on all these maps and understanding how all these elements correspond to different pigments and understanding the color of different pigments, what people have been able to produce was this particular figure, which is exactly what lies beneath the patch of grass. So the story goes, so Van Gogh painted this particular picture when, of a Dutch peasant when he was in the Netherlands. But at some point, he joined his brother, Theo Van Gogh, in Paris later, after painting this. Now, he took the picture with him, but he probably realized that this picture did not quite suit the taste of Paris people. So what he has done, being an extremely not very poor painting without much money, so he tended to reuse his canvas. So in fact, about 30% of Van Gogh's painting or so, these are from reused canvas. So on top of this, he has produced this patch of grass that apparently suited Paris tastes much better than the previous one. Thank you very much.